Hello, so in today's video, we're going to look at convergent and divergent geometric series. So yesterday we looked at convergent and divergent geometric sequences. We're going to now consider series. So series are when you sum numbers in a sequence. So a geometric a geometric series is when you sum numbers in a geometric sequence. So here are a couple of geometric convergent series examples. So we can see that this is a geometric sequence. So the sequence of numbers here is geometric. You're multiplying by a half each time. Your common ratio is a half. So this is certainly a geometric. These numbers form a geometric sequence, but when we add them up, this is a geometric series. And in fact, this is a convergent series because the sequence 1, a half, a quarter, an eighth will actually converge to 0. So eventually, because the sequence converges to 0, we're adding numbers that are getting smaller and smaller and smaller. So essentially, we're eventually going to add 0, which means that the sequence goes to 0. So we're adding basically 0 to the sequence. So the sequence stops increasing. The sequence will actually converge. Sorry, the series will stop increasing. The sum will converge to a proper number. And this one as well. So we've got a common ratio of this one of -3/2 each time. Times by -3/2. Sorry, let me write that again. Times by -3/2 times by -3/2. This is again a convergent. It's a convergent sequence because we're multiplying by a ratio less than with a magnitude less than 1. And we can see that the series is going to converge as well because the sequence of numbers here, here, and here are going to converge to 0. So when we add those numbers up, we're eventually going to get a convergent sum. But these sums here are divergent, actually. So again, these are geometric. So the numbers here are geometric, form a geometric sequence, but the sum is actually divergent because you've got a common ratio here of +3/2. But yeah, this is sorry, I've I've made a mistake here. Sorry, the common ratio up here is not 3/2. My bad. Sorry, this is -1/2. Sorry, my bad. Let me change let me change this. This is a -1/2 common ratio. -1/2. Sorry, my bad, -1/2. And this is a -1/2 common ratio here. So again, yeah, -1/2 has a magnitude less than 1. So this is a convergent geometric sequence, and when you add them up, it's going to be a convergent series. But this one here has got a ratio 3/2. Now that's bigger than 1, so this is actually a divergent geometric sequence and a divergent geometric series. Now this one here has an R value of 1, so when you times 10 by 1, you get 10 times by 1 times by 1. But this is a divergent series, so I mean, obviously when you do 10 plus 10 plus 10 plus 10, the series, if you do it for infinitely many times, 10 plus 10 plus 10 infinitely many times, it's going to diverge. It's going to get bigger and bigger and bigger and bigger. It's not going to converge to an actual number, unlike these ones here. These converge to an actual number, so we're going to get a number. I'll call it S for that. I'll call the sum there S, and I'll call this S here. But this is just going to get closer and closer to infinity, and this one's going to get closer and closer to infinity. So the first two converge to a sum. When you add these numbers, you get an actual sum. But when you add these sequences together, you get an actual. You don't get a number. You get basically you tend to infinity. So a geometric series is convergent if the common ratio R has a magnitude less than 1. So a geometric sequence will be convergent if the common ratio is basically less than 1, or less or small or bigger than -1 if it's a negative number. So for example, this geometric series here, so you've got 10, 9. So basically, to go from the first term to the next term, you're going to multiply by 9/10 times by 9/10. So the common ratio for this series here is 9/10. So the R value is 9/10. So 9/10 has a modulus less than 1. So the modulus of 9/10 is less than 1. So my claim is that when you do this sum here, 10 plus 9 plus 81/10 plus 729/100, and so on and so on and so on, this is going to equal a number. So this is going to equal some number. That is my claim. Yeah, so for example, the key thing to realize is that if a geometric sequence converges to 0, then the series is convergent. Now, this is not always true for every sequence, but this is true for geometric sequences. So if you have a geometric sequence that converges to 0, so for example, this sequence here. So the sequence 10, 9, 81 over 10, 729 over 100 will eventually converge to 0. This sequence is going to converge to 0 because the numbers are getting smaller and smaller and smaller. You're multiplying each number by 9 over 10. If you continue doing that infinitely many times, you're eventually going to get 0. So this is a convergent sequence to 0. So the sum is going to converge. So the actual sum is going to converge. So for example, so the nth term of this sequence back here, this 10, 9, 81 over 10, 729 over 100, has this nth term here. So the first term times by the ratio to the power of n minus 1, that's our nth term. And that's going to go to 0 as n goes to infinity. And that's because if we think about it, again, when we make n the power a massive number, 9 over 10 to the power of a massive number in your calculator, you'll get basically 0. So 0 times 10 gives you 0. So this is going to converge to 0. So the sequence will converge to 0. So that means the series 10 plus 9 plus 81 over 10, etc., etc., is going to converge to a particular value. So actually, we're going to look at how we work out that particular value in the next video, like how you work out the sum of a convergent series up to infinity. Because obviously you've got loads and loads of terms here, but eventually what I'm claiming is that the sum of all of these terms is going to actually give you a number. And again, I'll call this S, this sum S, where S is an actual real number. So when you add up all these numbers infinitely many times in the sequence, you're going to get a whole number. Sorry, not a whole number, a real number, a real value. However, though, if you have a sequence with a ratio, a common ratio bigger than or equal to 1, then the series is divergent. So if you have a ratio, obviously a ratio of 2, your numbers are getting bigger and bigger. You're multiplying each number in your sequence by 2. So your sum, your series is getting bigger and bigger and bigger. It's diverging to infinity, basically. And this one as well here. So 10, 10, 10, 10. This is a convergent geometric sequence. And that's because the sequence converges to 10. So this is a convergent geometric sequence, but it's a divergent geometric series. So the 10 plus 10 plus 10, the series, is going to basically go to infinity. It's diverging. It's not converging to a proper real number like this sequence here. 10 plus 9 plus 81 over 10 plus 729 over 100 converges to a proper real number because the sequence diverges to 0. So the sequence of numbers gets to 0. So eventually the sum is going to get to a fixed proper number. But this sequence doesn't converge to a fixed proper number, 10 plus 10 plus 10 plus 10. The series doesn't converge, it diverges to infinity. So basically, this is a divergent series when the common ratio is bigger than, has a modulus bigger than or equal to 1. But when you have a common ratio with a modulus less than 1, so 9 over 10, a half, minus 9 over 10, minus 0.1, the series will converge, and as will the sequence as well. The sequence will also converge to 0 in that case. So that's just a summary of how you can tell whether a geometric series is going to diverge or whether it's going to converge.